Hello and welcome back to another VMK in the game development series. In this VMK I'll introduce you into a new class for the math library. Now this video is not going to be very long because the class we're going to develop is relatively simple. And what we're going to be developing is the ability to store planes in 3D space. Now we've done something similar already inside of the object library to render a plane on the screen, and we called it flat grid. Well, now we're going into the math library to implement a generic plane class so that whenever we work with 3D objects and we need to do collisions with flat surfaces, we'll be able to use this plane class to do all of the math for us. So initially, we're just going to create this plane class to store structures that contain the representation of a plane. And again, a plane is just a 3D object that is represented by a number of points, and we can represent it by either 3 points or a vector and a point. And using this information, the constructor is going to construct all the sort of necessary information to create this plane for the mathematics to do all the processing whenever we need to do anything with a plane. Simple enough. Okay, so let's get started. Inside the math library, currently we have vector3.cpp and vector3.h. Well, we're going to be adding the plane.cpp and plane.h files into here, but before we do that, I want to add one extra sort of a pair of files. And what we're going to call these are general math. And inside this general math, this is where we're going to put sort of functions or classes or structures, anything that's sort of general in nature that we may want to use inside other classes that will go inside this math library. To do that, let's just right-click on the math lib and go Add New Item. We'll create a CPP file. And we'll also do the H file. The C++ file really isn't going to do very much other than include the generalmath.h. And inside the generalmath.h, we have the following. We include the stdafx.h, which is inside of our game. I think it was inside main here, stdafx.h, or sorry, that's CPP. The .h is located here. And we're going to define a constant, which I'm going to call 0_e5. And that's going to represent a floating point number with precision 1e to the minus 5. You'll see inside the math library, we'll do a bunch of comparisons with 0. Well, instead of doing 0, it's better to have an epsilon value to compare with, because when you're doing math calculations and numbers are being calculated for you by the processor, sometimes the values will go to a very, very small number, but not exactly 0. So to make sure that your game or whatever is able to recognize that this is close enough to 0, we're going to be using the 0 epsilon 5 value to represent 0. And then at the bottom here we have end if for the definition at the top. Let's just go and compile this and see what we get. Everything is fine. So we can close that off and go into the math lib here and add our plane.h and plane.cpp. The CPP file is going to be relatively simple again. It's just going to include our plane.h. So we can save that and close that off. Actually, I'll leave it open because we're going to build it in a minute, or compile it. And then the plane.h. Okay. At the top, we're including stdafx.h again, our generalmath.h, and vector3.h. The general equation for a plane is shown here. Ax plus by plus cz plus d is equal to 0. A plus B plus C represent the normal vector that points away from the plane. And there's actually two normal vectors. There's this one, A, B, and C, and there's also minus A, minus B, and minus C, which points down in the opposite direction. D represents where this plane crosses an intercept in 3D space. And we'll see how we use this A, B, C, and D values in a minute here in the plane class. So we have our class here called plane, and for the public, we have the following. Now you notice that I'm not defining my code inside of the C++ class like I do for most of the things inside of the scene, for instance, or object. Instead, I'm defining it directly inside the .h file. And I'm doing this for the purpose of being able to use this inline keyword. By doing inline, what I'm telling the compiler to do is anytime that I create a plane class, instead of making a chunk of code inside the executable that will represent plane that we can then go and point to, what I'm doing is I'm actually implementing that structure directly in line with the code wherever I'm supposed to be using plane. So this is going to create a larger executable file at the end when I compile. However, it will run faster. So I'm doing this for all of my math functions because I know that the math is going to be running multiple times throughout the game, and I want to make sure that I want the math to be calculated as fast as possible so it doesn't slow down my game. That's why I'm using the inline. Okay, so our general constructor for the plane is if you don't pass in any parameters. And if you do this, then what I'm going to do is specify that my member variables, well, I guess I should talk about the member variables first. Let's go down to the very bottom here and take a look at the variables for the plane. I have one variable, which is a Boolean, which is called m_bok, and I use this to define whether my constructor constructed this plane successfully or not. So if it's successful, BOK will be set to true. If it's unsuccessful, this will be set to false. So then outside the plane constructor, I can check whether the constructor actually succeeded or failed. Now, the constructor cannot return a value, so that's why I chose to use this method to tell me whether the constructor is succeeding or not. The other thing that I have inside this plane class are these two member variables. They're both vector 3s, and the first one is called point and the second one is called normal. The point defines a point in 3D space that lies on the plane, and the normal defines the perpendicular vector that points away from the plane. Let's go into PaintShop Pro and I can actually draw you what these mean. Let's grab a tool here. A plane in 3D space, let's say, is represented by something like this. So imagine there's some sort of coordinate system here, x, y, and z. Or I guess I should really be using the OpenGL coordinate frames. So this would be x, y, and this would be z. So if I have some plane in 3D space, the plane itself could be defined by a number of points and whatever. However, to define it inside the plane class, there's two ways to do it. Either one way is to specify what is the direction of this normal. So this normal is perpendicular to this surface, and give me a location that's on this plane itself. So I need a point, x, y, and z. And this is the normal. And the normal itself should be a unit normal, and if it's not, then I go and normalize it automatically anyway. So that's one way to define a plane. The other way is to give me 3 points. If you just give me any 3 points, like let's say these ones here, I will then go and calculate the normal for this plane, and then with that information I have enough data stored to then be able to use this plane in any sort of math that I require. Okay, so that's what we're going to be doing. Now let's scroll back up to the constructor here. So If you don't pass in any data for, then I'm going to create a plane so that the normal is pointing upward, so 0, 1, 0, meaning in the y direction, and the point on the plane is going to be 0, 0, 0. So in other words, what I'm going to do is in 3D space, let's say this is our 3D space coordinate system, here's 0, 0, 0, my plane that I'm defining is going to be like so that its perpendicular is directly pointing upward and it's laying flat on the screen. So if we're looking at it edge on, it would be like this. Now, one thing you should notice here is the plane itself has no boundary. It goes off to infinity in each direction. So there is no limit as to how big this plane is. In mathematic terms, it goes to infinity in every single direction. But the point tells you one location that's directly on it, and the normal tells you what's exactly perpendicular to the plane. So back in here in the constructor, we set the point to be 0, 0, 0, the normal to be 0, 1, 0, and then the last thing I do is just set the Boolean value here to be true to say that this constructor is done successfully. The other way to construct a plane is to give it a point and a normal, and if you do that, then I just take that point, set it to be the point inside of this member, as well as the normal, set it equal to the normal, and then I go and call the normals dot is 0. Now this function itself hasn't been implemented yet because it's part of vector 3, and we're going to go and implement this in a second. But basically I check to see if this normal is 0. If it is 0, then there isn't anything I can do, so I just go and set this VMK value to be false and I return. So in other words, this constructor failed because the normal value is invalid. I don't know which direction is up. If this skips the if statement, then I set the VMK to be true, saying that the plane is okay, and then I go and normalize the normal that was passed in here. And the normalization function was already implemented before, but we're going to go into the vector 3 in a second to clean it up just a little bit. The third way of creating a plane is to define 3 points. So point 1, point 2, and point 3. Let's go into PaintShop Pro here, and I'll show you exactly how this constructor is going to work. So let's say we're given 3 points, point 1, point 2, and point 3. Point 1, point 2, and point 3. What I'm going to do is create 2 vectors. I'm going to create this vector here, call this vector 1, and I'm going to create this vector here, vector 2. Using these 2 vectors, I can then cross them to get the vector that's perpendicular to both of these. Having this new vector, I can assign this to be the normal vector, and by choosing any one of these points to be the point on the plane, we now have the definition of our plane, because we have a point and we have a normal. So let's go take a look at the code. We're taking the point value and we're going to store it to be point number 1. So whatever you pass in here, that's going to be the point that is on the plane. You could choose any one, it doesn't matter. I've just chosen to use point 1. Now, next thing I do is I go and create these 2 vectors. I call it v3 vector 1 and v3 vector 2. The way that I define vector 1 is I take point number 3 and I subtract it from point number 2. That gives me vector number 1. Vector number 2 is defined by taking point number 1 and subtracting point number 2 from it. I then take vector 1's cross product with vector 2 to get the normal, and then I take the normal and I check it to see if it's 0. If it is 0, again, there isn't anything I can do, so I set this to false and I return. This would only happen if these points that you pass in here are not unique, or in other words, they're perfectly aligned so that they form a straight line. If you do that, then there isn't going to be a normal here. But if you give me any other 3 points, then I will be able to find a plane, or actually a normal, to those points so that I can define a plane. After that, we go and set the Boolean value to be true, and we normalize the normal so that we have a unit normal. We have a virtual destructor which doesn't do anything, so it's blank. And the last function that I have here is getNormal. And getNormal will just return a normal that's stored inside of this class. Now remember, the point and the normal here are private, so from externally you can't access this guy or this guy. If you want to get the normal for whatever reason, you have to use this function. And if we ever need to get this point, then we would have to write also an inline vector3 get point function so that we can return that point. But we're not going to be needing that for a little while, so I've just left it out for now. I've only implemented the functions that we're going to be using in the next video. So that's pretty much all we need to do for the plane.h, but before we can compile this code, we need to go into the vector3 and make some modifications so that we can include this is0 thing and we can clean up some of the other code that we have there for now. So let's go take a look inside vectors3.h. And okay, the constructor's fine. This one's fine. Let's just scroll through here and take a look. We have a bunch of operators. We have the plus, the minus, perpendicular. Okay, we have a cross product here. I'm just going to clean this up so it's a little bit easier to read. It's the exact same formula. I'm just cleaning it up. The nice thing about C++ is it doesn't care about these extra spaces here, so you can clean up your code to be more easily readable by doing the following, and you don't have to scroll all the way across to read the functions that are inside here. Now, we have the normalize here, which we go and have fmag, which is the magnitude of this normal. We go and calculate it by taking the x squared plus y squared plus z squared and then square rooting it. And then we check to see if fmag is less than 1e to the minus 6. So this is effectively 0. Now you'll remember that back inside the general math we created this function, or this constant floating point number. What I'm going to do is replace this 1e to the minus 6 with this 0e5, which is 1e to the minus 5. Doesn't matter if you use minus 5 or minus 6, they're both pretty small, so it shouldn't make a difference. But I want to use this constant because the constant is a little bit more robust, so that if I did want to change it later, I can just change it all in one place. So we do that, and then down here, we're taking each of these values and dividing it by the magnitude. Well, there's actually a little bit faster way of implementing this if we were to do the following. We can go fmag equals 1 divided by fmag. So we're taking whatever this calculation is, we're inverting it, so now fmag is equal to the invert of that, and now what we're going to do is take the x value and multiply it by fmag. So we're still performing the exact same operation, but now we're doing the division one time, and then we're multiplying by these three values rather than doing 3 divisions. Usually processors in the computer are able to perform multiplications faster than they're able to perform divisions, so that's why I've swapped the order of these calculations here. I did the one division only once, and then I did a multiplication 3 times. Okay, and we need to go and implement the is0 function. So just down here, we have inline bool is0, and it's going to return a constant. So we have if the absolute value of x and the absolute value of y and the absolute value of z is all less than the 0e to the minus 5, then effectively this vector is going to be 0. So we just return true, meaning it is 0. Otherwise, we're going to return false. Okay, let's go and open up vector3.cpp and compile this. It's complaining here because it doesn't know what each5 is. We can fix that just by going and including the general math.h. Oh, that should actually be included in the .h file. Right up here. Well, I pressed build, so it's building the entire project rather than compiling the sections that I wanted to show you. But we do have some problems. So let's go back into here, compile this code, and vector3 seems okay. And then let's go into the plane and compile this. And this is the one that's having problems. So we haven't defined a minus operation for two vectors. So we have vector3 minus a vector3. It doesn't know how to handle that because it's really trying to take the binary negative of this guy, but it doesn't know what that means. Well, we can go and implement that as well inside the vector3 class. And I'm going to open up the class view here for math vector3. Let's see, we have the operator minus equal, we have this operator. So I'm going to put it right above this guy. So what we're doing here is we have inline vector3 operator minus, and it takes in a constant vector 3 here, when it's going to return a constant vector 3. So when we go and return, we return a vector 3, and it's going to be the value that is for us minus this value that was passed in for the x, for the y, and for the z. Save that and go back into the plane.cpp and compile this. Okay, and that succeeds. And now if we go and do a build for the entire project, it should build successfully. Okay, I think I did see some warning messages. Let's just go and see what those were all about. Okay, general math, warning, link 4221, no public symbols found. We can go and fix this by, well, first of all, the reason why we're getting this is because inside math.general math, we've created a structure here that only has a floating point number, but inside of the, where is it? Inside of the general math.cpp, we don't have anything here. So to get rid of this warning message, we can do the following. Just down here, I'm going to create a math dummy function, and this is just temporary, so it's going to get rid of that warning message. And inside the .h file, I'm just going to create this dummy function to get rid, or it's a dummy function prototype to get rid of that compiler warning. So now when it goes and builds this project, the compiler knows that there is this function, and inside here there's a prototype, so we won't be getting this linking error. We have also the same problem with vector 3, because inside vector 3, let's see what we have. In here we don't have anything, and all of our code is implemented down here. So to correct that, we can just go into the vector3.cpp and put our destructor inside of the CPP file. Since it's not going to do anything, so it's not really going to slow us down, we can place it in here, and then inside the .h file, just want to make sure that the default destructor isn't implemented in here. Instead, we just have the prototype for the destructor. So now we'll just rebuild the project, and I think those two warning messages should be gone. Let's just scroll through here. 00, 00, 00, 00, 00, 00, and 40. Okay, so that cleaned everything up. So now we have a generic plain class which we can use, and in the next video I'll show you how to implement a new geometry for our OpenGL game, which will be able to use this plain class for some pretty important